Wow, thank you, Ben. That was really a great introduction. And I'll admit, I always get nervous when people clap at the start of a talk, so hopefully you'll clap at least as loud at the end. So how do we get this up and rolling? I'm an academic, I can't speak without PowerPoint. As a side note, it's true, I proposed with PowerPoint. It worked out, she said yes. We're still married. Well, maybe I'll start with where I was going to on a bit of a tough note. There's some pictures. I don't know if people knew him, but a great light in the salmon world and in the research world and member of the Kenai was lost recently. Steve Okinen died in a tragic accident. Steve was a colleague of mine at the University of Alaska in the College of Fisheries Ocean Sciences. He was an incredible researcher. But much more than that, he was a dedicated father, husband, married into the Jakinski family, was deeply connected to this place and the fish. And in the words of a past president, the streets of heaven are too full of angels today, and Steve's going to be missed. So if you can keep Steve in your thoughts, it was really a tragic loss. So I'll transition into what I really want to spend time talking about, but with a disclaimer that what I'm going to share certainly is not mine alone, that the lessons I'm going to share have emerged out of years and years of work, hundreds of people, tons of people thinking about these things. What I'm trying to pull together and synthesize has been melded and shaped really by the thinking of the three people on the top, myself is one of them, but Daniel Schindler and John Moore. John Moore is at Simon Fraser University. Daniel Schindler is at the University of Washington. And we are the sort of the core part of a project that's going to be a focus of someone I'm going to talk about. But what I'm sharing is really sort of a joint effort to try to synthesize some key lessons of what hopefully people can take away from sort of the current state of salmon conservation science. So I want to spend a little bit of time talking about this project. It's the Salmon Science Network, but we call it SalmonNet for short. salmonnet.org, you can check it out. So what are we trying to do and who are we? So our mission is trying to catalyze salmon science across the North Pacific, international science research. It is a legacy grant that came at the end of a massive period of investment in wild salmon research from the Gordon and Betty Moore Foundation. They were finishing their efforts and thinking about how can we try to leave something that might have some enduring stay power, and SalmonNet was one of their sort of wrapping up legacy grants. So some of the things in which we do, a core part is trying to make science not only freely available, so often papers that are published get locked behind closed barriers that you have to either have a credit card to pay for a paper or have access to an academic institution to get past a firewall. And so we make papers freely available for downloading, but we also, in these what we call science spotlights, is that we translate the science that inherently from a peer-reviewed publication still is fairly jargon and written for experts, translate that into language that is hopefully more digestible, interpretable. And because we have a real hyper focus on trying to make this available to researchers across the North Pacific, we work with an amazing woman, Victoria Chilcote, who translates these spotlights and the other materials we produce into Russian. And a huge amount of our following, by clicking here, if you're any Russian speakers, you can click and the website and materials become Russianized. There's a lot of really excellent researchers in Russia that are doing their best to modernize, use current science, and are working in the worst of conditions. And so we are continuing, despite geopolitical challenges, trying to still work with people that really have the best of intentions for resources that are really very similar to ours, that are facing many and essentially all of the same challenges. So that's a core mission of SalmonNet. So you can zoom in. This is just an example of what one of the spotlights looks like. So each paper is sort of summarized. It's in a nutshell where we try to distill it down. We actually work with science writers that are trained to actually do this. It's a really hard thing, is to communicate science as taken from an expert and make it understandable. So you can download the paper, and then also you can click the authors that we work with. They provide slides, they provide photos, pieces of their work that if you want to take their slides and show them at a presentation like this, you can use it. So there's a bunch of resources. Anyone looking for good salmon photos, right? So we've also compiled these. So if you go, they're freely available: fish, wildlife, people, landscapes. Have permission from the photographers, the content creators to post these. Just give them credit, but free to use. Please use them widely. Fish images. And we're always accepting donations, and also can support with modest, reasonable amounts to support photographers and content creators with materials. Okay. Another big part of what we do is trying to catalyze and bring people together to talk about pressing issues. So we sponsor and host workshops. And what I'm going to talk about today is really what has emerged out of a workshop that happened essentially just pre-pandemic. So in October 2019 at an AFS, American Fisheries Society meeting in Reno, where we brought together people that was based on a kind of a crazy idea that I had to the team, was asking this question of, what do you think the big ideas are from our generation or whatever that's really shaped what we do? What are those big ideas? And so we started, jotting down a list. How many are there? Getting people together. Who should be in the room? It's not always exclusive, but complete list. But it was really fun to start distilling down, what do we think these key messages are? And back to the title of my talk, starting to sort of envision like what are the lessons that maybe we can glean from what we've learned in this past generation of salmon science that a new manager, tasked with managing some watershed anywhere, what are the lessons that they should know? I mean, I do get calls from people who say, hi Peter, I'm from so-and-so and I'm on this river and I'm new to Alaska and I'm the new manager that's here, and what should I know about salmon? Like, oof, okay, right? I mean, I get those calls. So sort of taking that hypothetical of what should managers know? And lessons not just from Alaska, but from across the North Pacific. So this is a bit of what the room looked like, not too different than this. Packed house. This is Carrie Naish from the University of Washington talking about the interactions between hatchery and wild fish to this group in Reno. So what came out of that is from this meeting are these 5 key principles that are going to form most of what I want to share with you today. And I'll start with the first one. So the first one being that all habitats have finite capacity. Okay? That salmon are regulated by habitat-specific density dependence. First jargony term, what does that mean? It just means that population growth and the abundance of populations are regulated and controlled by how many individuals are in that population. Said another way, there's competition for limited resources. There's competition for space. There's competition for food. There's times where there's competition for dissolved oxygen. That all habitats, regardless of where they are, have some inherent habitat-specific capacity, and it's finite. We can see what happens when habitat exceeds capacity. Salmon, like all species, have the capacity to grow exponentially and outstrip the availability of resources. This is a small creek in Bristol Bay. I've been up and down this creek countless times. It's called Hansen Creek. It's been walked essentially every day of the spawning season for decades, part of a long-term project from the University of Washington. In 2014, this 2-kilometer-long stream had over 60,000 sockeye spawning in it. So this is a picture of a core spawning area that usually in a typical year, there would be pairs of fish paired up on nests spawning, and that's what it looked like. There's no space. And so what happens when there's that many fish? Well, most of them keel over dead. Oxygen gets depleted out of the water. There's competition for space. Most of the fish keel over dead without spawning. So this is an example, a lot of the females die fully unspawned, and then there's a lack of space. A lot of fish still do spawn, but there's competition for space, and we can see this, we can observe it. And so this exceeded habitat, you can see the evidence of this in this pre-spawning mortality. We generally see the lessons that the most abundant, densely spawning species tend to be limited by spawning habitat. So pink salmon, chum salmon, sockeye salmon spawn in really high densities, like the picture I showed you. There's a picture from Prince William Sound, pink salmon. that they generally are limited by, the populations are limited by how many fish they produce in terms of the available habitat for spawners to spawn. The amount of gravel, the amount of stream length. It's because their juveniles are gonna leave those streams and go to areas that have larger capacity areas, like large lakes or oceans, right? So these species tend to be limited by rearing or by spawning habitat. In contrast, the least abundant species, like coho, Chinook salmon, steelhead, tend to be limited by rearing habitat. So those juveniles are gonna spend multiple years rearing in freshwater habitats. So if you think about how many fish a system can produce does depend on the basic habitat capacity of the system, but also the life histories, the species that are there. And generally speaking, coho and Chinook and rainbow trout, steelhead spend a lot of time in freshwater. They're going to be limited based on the rearing habitat. And we can see this play out places like Little Creeks in Washington. This is just one little snippet from a review where they look at the relationship between the numbers of spawners per kilometer river on the x-axis and the number of smolts that are produced in that kilometer river. And you see very quickly you come to some asymptote flat level where if you add spawners, you really don't get very many more smolts. Evidence is that there is capacity for those systems to produce smolts. And as you would expect, the most clear sort of predictor of how many smolt coho salmon comes out of a river is just the length and size of a river. So the longer the river, the more area you can produce more smolts. But it's a good reminder that adding more adults, if habitat is limiting, is not going to give you more offspring. Habitats are limited and are finite. Density dependence and this idea that competition sort of governs the world is really what forms the basis of much of fisheries management. And the idea that our goals for maximizing return or yield is going to happen somewhere intermediate between really high levels of spawning and zero levels of spawning, such that our goals often, if we wanted to maximize our long-term yield, is going to be in these intermediate zones that maximize the difference between return and the replacement of individuals. And we talk about these factors being sort of these compensatory factors. So it is to say that there's competition occurring and that per capita, individuals start doing worse as individuals increase in the population, right? More and more population builds, individuals do worse, there's more competition. And so at this level, there's no yield because they're at carrying capacity. So if some intermediate values is where your theoretical return could be maximized. And this is what forms the basis of fixed escapement goals and so forth, is this idea of density dependence that is rooted in this idea that all habitats have finite capacity. There's also this interesting idea about overcompensation, this idea that when you get so many spawners, that in the future you're gonna do worse because they compete with each other and you're gonna do way worse in terms of this overescapement. Well, when you go looking and ask what the data actually tell us, this idea of overescapement, really high levels that you end up doing worse, is not really borne out from the data. So people that see stock recruit curves, this is pretty typical. You get more or less a shotgun blast of data. And if you fit curves to this and allow it to be flexible, have it either bend over or be flat and asymptotic, usually there's as much evidence for it being flat and not bending over, not looking like overescapement, than the other. So there's a lot of talk, certainly in the general sense of things, that if we let in too many fish, we're going to do worse in the future. And the data does not bore that out. So while overescapement may be an economic thing, there might be sort of impacts on yield in a given season, you're not going to be impacting your productivity long-term in a system if you let in a lot of fish. We know that too from paleoecology. You can go back and actually core lakes and reconstruct the number of fish based on isotopes in the sediment of the lakes. And so if overescapement was really happening back in the day when there was no fishing and there was constant overescapement, you would expect lower number of fish than we have now. And the evidence just does not support that. So as a manager, don't fear overescapement. All right. There's also evidence that the ocean, just like all habitats, is also finite and can be limiting. So it was not that long ago, I went to school, and the ocean was taught to be a black box and limitless. I mean, was taught by people that knew what they were talking about, and the evidence was that at the time. And neither of those are true anymore. So we see signals of competition at sea in these 4 little plots represents over 12 million individual recorded salmon. This is from a paper led by a postdoc, 2 postdocs essentially, that got married. I'm not giving total credit for myself for that, but a little bit of a matchmaker. So Curry and Krista, 12 million records from ADF&G, blood, sweat, and tears over the years, bringing this together to say, how has the size of salmon across Alaska changed through time, right? So we're just plotting the mean size of the fish. These are the 4 species that we have data on. As it turns out, Alaska doesn't keep great records on pink salmon, the most abundant, thinking that they're all the same. I assure you not all pink salmon are the same, but point being, we don't have data from pink salmon. But what we see in these plots are some remarkable consistencies of periods of times where there's declines and recoveries and dips and recoveries, and all of them show, to different degrees, rapid declines in size, certainly after about year 2000. And when we do the analyses, when you ask, how can we explain these patterns, right? You have hypotheses about temperature and about fishing and about freshwater flow during different life stages, right? You can ask all these questions of how do we explain it? This analysis and a lot of other analyses that are done independently by others using similar data sets, different data sets, what emerge out of this and other data sets is that the most consistent factor that what we find to explain the ups and downs is the abundance of Alaska-based pink salmon that are in the ocean in those years. Is that a causal, mechanistic relationship? Don't know, but it is directly consistent with this idea that habitat is limited. There is competition. And so when there's a lot of pink salmon, these other species tend to be smaller in size. So which raises this idea that there very well are not only limited capacity, but potentially trade-offs to be thinking about in a world where there are so many both wild pink salmon, but also a lot of hatchery fish. And we'll talk a little bit more about that. Okay, so I'm going to shift gears a little bit and think more about the habitat itself. And the next principle is that habitat is complex, hierarchical, and dynamic. Salmon have evolved in really variable, heterogeneous landscapes that are blinking on and off in suitability across time and space. And so this is just a snapshot, give credit, this is another slide, but from Daniel, from Bristol Bay, where you have, for example, this little creek, aptly named Berm Creek, that for periods of times when the lake and the ice is just at the wrong conditions, a berm forms at the mouth of the creek. Fish that had gone to sea 3 and 4 years ago show up home trying to get home, and there's a berm. And they end up hanging out in front of the berm until they keel over dead, right? So that site becomes no longer suitable. Similar fish here that were spawning during a high flow event, the river dropped. These are all fish nests that have gone dry, right? So that in that year, that site had been looking good and then it blinked off. Beavers come and go. They're busy. They build, dams break, blinks on and off, habitat waxes and wanes in these systems. Systems where the lake level goes up and down, and creeks like that shallow little creek, Hansen Creek, that I told you about. Years when the creek is really low and dry and fish struggle to get into the creek. Other years there's lots of rain and they swim right in, right as rain, right into usually to the mouth of a bear, but that's another story, okay? So the idea is that salmon have evolved in this patchwork mosaic of habitats that are good and bad, blinking on and off in suitability. What might be good now might not be good 5 years from now. What's good for one this year might be not good for another. And we can see this in a bit of a cartoon, where if we have a typical, sort of archetypical river scape, where you have fish coming and going, you have a big main stem river, a lake, and some tributaries. You could consider it like the Kenai, right? You have a main stem, some lakes, tributaries, and climate change is pushing down on this system. There's these external forces acting on this system. But what fish experience in any given habitat is filtered through the conditions of those local habitats, right? Because a tributary, a lake, and a main stem all have their own suites of physical, chemical, ecological processes that then shape the genetics and the outward appearance, the phenotypes of the fish that are in those environments. So this idea that some streams are going to be more sensitive to global warming than others, that's right. And the fish that are in certain types of streams that are more sensitive are going to experience climate in a different way than fish that use a main stem river that are buffered from things like glacial snowmelt. So climate does not impact all populations the same. It's filtered through this idea of local habitats. And because they're in these local habitats, these patchwork of habitats, what's good in one year might not be good in another. What we see, just like a complex portfolio where you're better to be diversified, is through time, these three habitats, a lake, tributary, or river, are waxing and waning, essentially marching to their own drum. They're asynchronous, just like you would hope from a diverse financial portfolio. So the idea is that what happens is overall the production from this watershed as a whole that's comprised by these constituent parts become buffered against the ups and downs. The variance of the numbers of salmon is buffered because you have this diverse intact habitat and it's reflected in the life history and the returns of the fish. We can see this empirically. This is beautiful work by Sean Brennan, who also tragically died way too young. He was a skier and died skiing just a couple of years ago, leaving young kids. I mean, he was younger than I was. But some of Sean's incredible work, he did his PhD at University of Alaska Fairbanks, worked with Daniel at UW, but he was using the chemistry of the ear bones of salmon to trace where the fish had been rearing during their juvenile phase and looking at the turning adults that had survived to look across years to say which habitats actually produced the returning adults, right? That's critical habitat. Fish use different habitats, but which habitats are actually producing the fish that are coming back, that can be harvested? And what he shows, consistent with this idea of a patchwork, a mosaic of habitats, is that in these maps, just look at how the colors vary across years. It's blinking on and off. Some years it's this, and some years it's this stuff. It's variable. And so having this patchwork, these options for fish to be rearing in these different areas provides this buffering resilience in the face of change. So this plays out at these scales, and we've seen it play out at larger spatial scales and temporal scales from things like the paleoecology that I was mentioning. So this is very real. This is more than just a cartoon for a keynote address. This complexity also provides options for wildlife. So this is an example of looking at the timing of sockeye salmon spawning, again in Bristol Bay, and the timing of sockeye salmon spawning is intimately tied to the temperature of their spawning streams. Cold streams, fish spawn earlier, because in cold streams it takes longer for embryos to develop. Therefore, a female needs to spawn earlier to have enough time for development to occur such that her offspring emerge at the right time the following spring. So if you have a landscape that is highly variable in temperatures, what you see is this emergent property that you have this great spread in the timing of adult spawning sockeye salmon, which provides options for things like mobile predators for birds and bears and rainbow trout to essentially move across the landscape, hit up the early populations first, move to the middle populations, move to the late populations, and spreading out the amount of time to have this resource that comes from the ocean. Local fishes, bears can eat the salmon carcasses, the eggs. It just fuels this ecosystem. The amount of time is greatly spread out with huge amounts of benefit for wildlife because of this habitat diversity. So it provides options that would be lost if you had put all your eggs in one basket, say that you had just invested in the big rivers, let the little streams go, right? You would have lost months of available time for wildlife to be taking advantage of salmon resources. But beyond the wildlife, straight up, this complexity directly benefits people. There are both more fish and more reliable fish when the complexity and diversity is intact. We see this play out. See it play out in Bristol Bay and across Alaska in different fisheries. So as a manager, when in doubt, if anything, you should always be managing for diversity, always working to protect diversity. And thankfully, I mean, the bright side is Alaska still has so many options open. That's why I remain cautiously but audaciously optimistic that we have our options in place that compared to other places, Alaska has not gone the way of the lower 48, at least yet. So this is just a snapshot of the human footprint. You can tell, so reds and yellows are a lot of human activity. Dark blue is essentially nothing. So you can see the contrast, and it's pretty obvious. And in a place like Soldotna, Kenai, you can feel those pressures. So it's trying to strike the balances. But we have these options still on the table. And I think the lesson should be, as managers, practitioners, is how do we make decisions that maintain those options for wildlife and people? And of course, the salmon. So the next transition into thinking about these sort of patchwork of mosaics of habitat that are used is this idea that salmon exist as metapopulations. So what is this? Talk about jargony. So metapopulations is fundamentally just the idea that salmon exist in these sort of patches of suitable habitat across landscapes that otherwise are not suitable, right? So they have to swim through big glacial rivers to get to a clear tributary. That's where they're trying to hang out, right? So they have these sort of patches that are connected, and that individuals that do well in these patches tend to return there, which is to say that they become locally adapted to their home streams. I already showed you a picture of the temperature, right? Cold water, earlier spawning, that is a hallmark example of local adaptation to those conditions. If individuals get it wrong, they tend to be selected against. So they exist as these patchworks where individuals return to those patches and become somewhat reproductively isolated from individuals in another patch. Makes sense, right? Fish from the Kenai River tend to spawn with Kenai River fish more than they do from the Kasilof. But there are some individuals that move between patches. The jargon of this in the salmon world is straying. So not all individuals home back, but some do stray between patches. And the straying of these individuals is like the glue that holds these metapopulations together. Why is this important? Well, straying facilitates the colonization or recolonization of these patches when they blink off, right? So I said that salmon have evolved in these heterogeneous, diverse, dynamic landscapes. Imagine a landslide, a volcano blows up, whatever it is, that patch becomes unsuitable. Those fish blink off. Over time, it becomes resuitable again. Things work its way out. Those individuals from other patches stray and recolonize that patch, right? And so through time and space, salmon are existing in this sort of dynamic tug of war between colonization and extinction. And we're just seeing the snapshot of that. But this process of acting as a metapopulation that has these processes in play is a fundamental aspect of salmon ecology, biology, and should be taken into account and preserved. Straying also mediates, while it's fascinating for evolutionary ecologists like me, it also facilitates both the flow of individual fish, but also the genes that they carry. So if individuals are locally adapted to certain sites, individuals are moving around carrying those genes and those traits, it is a fascinating look at how this biological phenomenon shapes the evolutionary trajectories and the ecologies of these patches. We can see this play out. There's lots of examples. So this idea that salmon exist between this balance between extinction and local colonization. Hell's Gate on the Fraser River, British Columbia, they were building a railroad along this rapid. I don't know if people have been to Hell's Gate on the Fraser. If you haven't, you've got to go. It is fascinating. So this was always a wickedly difficult area for salmon to migrate past. Super strong currents, deep water, always tough. And building a railroad in the 1910 up the watershed, it made it even worse. There was a landslide, pinched off extra amounts of the river, and extirpated pink salmon above Hell's Gate. Pink salmon are smaller, they have less capacity to swim fast. Sockeye and Chinook, steelhead, they got past. No pink salmon above Hell's Gate for essentially a century, better part of a century, until they built a fish ladder, and lo and behold, quite quickly, pinks have recolonized, dare I say exploded, right? But there's lots of fish in the Fraser River. So again, showing essentially the resilience, the capacity of salmon when habitat becomes real available, suitable again. The dynamic of strain allows recolonization and often really rapid recolonization of newly available habitat. Closer to home, we can see this play out in places like Glacier Bay, where really essentially in our lifetimes, or our parents' lifetimes, glaciers have been retreating and creating new habitat in the form of streams. This is Wolf Point Creek. It's been studied since the 1970s by Sandy Milner and his crew. They've been walking and surveying these streams every year, cataloging, documenting, quantifying the colonization process of things like invertebrates and alders. And lo and behold, within the first couple of years, pink salmon, sea-run sockeye, dolly varden showing up in these new sites. So again, this idea that there's this patchwork of habitat blinking on and off. Some of the best available habitat is lurking under glaciers that are just now retreating. Places on the Lost Coast, Malaspina Glacier, unbelievable habitat is lurking under those glaciers as a bright spot. There's a lot of habitat that's going to become available. As long as the ocean remains suitable and available for the rest of their life history, there could be good things that come from that. So there's goods and bads. But the point being is that this strain is a fundamental process that leads to the recolonization of these sites. So strain is a fundamental biological process. It is also a process that does provide a mechanism by which you have the interaction between hatchery-produced, domesticated fish and wild stocks. And in places like this, in Patagonia, where Chinook were introduced in the 1970s, they have very quickly strayed and colonized. And if anyone really wants to catch a large-bodied Chinook these days, I recommend considering Patagonia. They're doing well. So I want to spend a little bit of time thinking about the other aspects, not necessarily just limited to strain, but thinking about the interactions between wild and hatchery fish. So Alaska is leading the world in terms of many things in fisheries. And one of the things we're really good at is we're really good at producing lots of little salmon to release into the ocean. So Alaska releases about a third or so of the 5 billion plus fish that are released into the North Pacific each year from across the Pacific Rim. This is just a snapshot of how things have changed since hatcheries really ramped up. Well, I was born like here. So right when I started, it has really ramped. And it's really dominated by a couple regions. Prince William Sound is a pink salmon producing region, and Southeast Alaska is a chum salmon producing region. Okay? And that hatcheries are absolutely an ingrained, entrenched, fundamental part of the fishery fabric in Alaska. And so much of what we know comes from the well-designed marking of hatchery fish, from altering the temperature during the development stage. This is a picture of the ear stones in a fish, that you can produce sort of these marks that allow us to distinguish that that fish is a hatchery fish and it came from a certain hatchery. So it allows us to keep track of hatchery fish in the harvest, and it also allows us to keep track of things like strays on the spawning grounds and so forth. And one of the problems, though, that certainly hatcheries have been effective producing lots of fish. It's a really important part of our fabric, but it does come with risks. All rewards do have risks. And one of them, this is a perennial challenge for a manager working in a system if there is a hatchery component and a wild stock component in a fishery, is that you have this mixed stock fishery problem, right? So if you have wild fish that are typically less abundant and less productive than a hatchery stock, if they are co-mixed and co-mingling, migrating at the same time as a hatchery stock, how do you maximize your harvest on the hatchery fish without over-harvesting the wild fish? That's the question. Because we know that the hatchery fish are designed such that we could catch, say, 95% of them, right? You don't take that many brood stock to make more hatchery fish. So we could harvest 95% of them sustainably, but really the wild fish could only be harvested at, say, half, 50%, right? So you either have to forego a lot of yield on your hatchery fish, which is to say let a lot of the hatchery fish go, or you're going to impact the wild stock and potentially overfish the wild stock. And this plays out. This is a very real challenge, and we see it literally by managers working in the field. Say managers face the dilemma of restricting fisheries to allow wild salmon run entry while simultaneously maintaining effort on salmon to reduce strain. That's another one. So they're co-mixing. So do you fish really, really, really hard on the hatchery strains to also keep them from interacting with the wild fish. Because hatchery and wild fish together are a massive manager's dilemma. I think this is an interesting one. Thinks dollars and cents. So this is from work from 2013 to 2015 that shows that even if you had this massive amount of effort to say, okay, well, let's just catch all of the hatchery fish, don't let them stray. Well, we can't catch them all. So 2013 to 2015 in Prince William Sound, there was an amazing amount of accounting that went on that allows us to actually calculate and estimate that only 1%, less than 1% of the hatchery fish strayed. So fishermen caught 99% of the returning hatchery fish. And that was sustainable. Like, it doesn't take that many spawners in a hatchery to produce offspring. Only 1% strayed. But arithmetic tells us that less than 1% of a really large number can translate into a really large number. So that less than 1% translated into about 5.5 million strays on the spawning ground. And for fishermen that otherwise should be catching those fish, strays are directly lost revenue. Hatchery fish are designed to be caught. And so for fishermen, over those years, they lost about $4.5 million of catch. Okay? So there are real consequences both for management and a whole host of other things that would be worthy of another keynote of thinking about the ecology, the evolution, the other parts of the consequences of hatchery and wild fish to be considered, but also have very real financial trade-offs. We've also are looking through a multi-year collaborative large-scale project with industry, the Alaska Department of Fish and Game, the Alaska Hatchery Research Program, asking the question of how hatchery fish might be impacting the productivity of wild salmon. So this is like a decade-long project. I'm on the science panel. Sam May is a postdoc working with me on the science panel. And so what he is showing using data and modeling, because you have to model things, is that what you can lose very quickly is the amount of genetic diversity of the wild stock. So on this axis is the proportion of your wild ancestry, and this is your amount of hatchery fish. So what this is showing essentially is that as the generations march on, very quickly wild populations can look more and more like hatchery ancestry, that genes from the hatchery can very quickly be introgressed and co-mixed with the wild stock. And we're exploring this across ranges of strains. So what fraction of the wild fish are comprised by strays? So, and this is parameterized with data from the spawning grounds and thinking about the scenarios that are going on real time. And so this is one of the consequences that we're seeing, that if we care about the maintenance of wild genetic diversity, it's something that it seems like we might be losing very quickly, even at fairly modest and observed levels of strain. And ultimately, I'll just leave with this for the hypothetical manager, that at the end of the day, if hatcheries were the solution to the problems of salmon, we wouldn't have problems anymore. We just would know that. And it's just not a solution. All right, so I'll shift gears on the, how am I doing on time?
15 minutes.
Oh, nice, okay. So I'll shift gear into this last bubble. And it's one that is maybe a little uncomfortable, but another truism, that our ability to restore degraded habitats once we've lost it is really limited. So if only it were so easy as like cutting along the dotted lines. This is my favorite bit of environmental activism graffiti of all time. It's really difficult to restore habitat. And what we have learned in particular is that we haven't appreciated until recently the legacy effects, the time scales at which these disturbances play out. And things like logging. There's a picture of a little guy looking at the logs floating down an coastal Oregon river that had been result of a splash dam. I don't know if people are familiar with splash damming. Back in the good old days, you'd form sort of temporary coffer dams, pile the logs behind the dam, and when they had enough logs ready to transport down to the estuary, they would break the dam, and in a rush of water, sediment, and logs would go torrенting down these watersheds, not only moving the logs, but everything else that's in that river would be moved downstream. And so the legacies of a lot of these coastal streams in Oregon and Washington and other places, that they're scoured down to the bedrock. The sediment has been totally changed. The amount of large wood obviously has been logged. And what we see is that for things like coho salmon, that really we're still seeing the effects of this for decades after logging has stopped. We've seen in a different system, in the Crown of the Continent area where rainbow trout have been introduced and interact with wild cutthroat, that there was massive stocking of non-native rainbow trout for anglers, fairly well-intentioned, but even after the hatcheries have been turned off decades ago, largely due to climate change and changing flow dynamics, that the hybridization, the interaction, genetic interaction between rainbow trout and cutthroat has actually increased in time. So even though they've been turned off, we are still dealing with the legacy, the long-term effects of these things that can actually accelerate after they've been turned off. So what to say is that it's really hard. Once you have modified a system and things are going a certain trajectory, it's really hard to redirect the ship. Often restoration ignores root causes and is done at too small a spatial scales. So I would imagine, like me, and some of you have probably been involved in these very well-intentioned activities to go to a local river and plant some trees or root some logs in a river. And often that is just missing the real cause of why are we doing this? The processes that have led to where the river is now at, needing restoration, has been ignored. That rooting these trees in this otherwise pretty degraded river is probably going to have marginal effect. In fact, I would argue, and not argue, evidence suggests it may have very short-term localized effects where you could increase abundance in this stretch of river, right? Because it shows that little fish like wood and pools, but it does nothing to increase the productivity at the scale of the watershed. So well-intentioned, done at the wrong spatial scales. And so there is a big movement to take on this idea of process-based restoration. So what has been lost are these fundamental processes of, say, flow of water and sediment transport and interactions between floodplains and groundwater, surface water interactions. Those things have become disrupted or lost. How do we restore the processes such that we are not stuck in this perpetual year after year having to do something? How do you set a watershed on the right course, restore the processes that it can heal itself? And from this movement, there are some other principles that are useful to think about in terms of process-based management. And the first one is address the root causes of the problem. This is one of the most fascinating ones from a friend and graduate student that was working on things for her PhD, and they figured it out. So every fall in the urban area of Seattle in particular, you'd have a first rain. Of course, the first rains bring in the coho salmon. They're waiting for the first rains to spawn in these little streams. And what happens? They keel over dead. Urban runoff mortality syndrome. It had a name. And what was it? And so lo and behold, they have figured out that it actually is the leachate from tires. There's a compound in tires of cars that are completely toxic to adult coho. And fascinatingly, adult chum that spawn at the same time in the same streams could care less and are like, whatever, don't even notice it, right? But for coho salmon, that's the root cause. So there is a directly actionable policy action, right? Is change the compound in those tires. Have local bans, right? I mean, there's all kinds of things that become directly actionable when you have found the root cause of the problem. Okay, so root causes are great. Oh, and I should have said this a lot. I've been highlighting as I go. Some of these are spotlights from SalmonNet. So if you're interested, you can go to the website, download the paper, look at the interpretation, blah, blah, blah. So I've been trying to highlight some of those. I should have said that earlier. Okay, the other principle too is be consistent with the biophysical potential of any site and try to unleash it and untap it. So this is just an example of trying to reconnect the lateral connections of main stem rivers, as in California, Sacramento, San Joaquin, rivers that have been greatly degraded. People have not seen those former powerhouse of rivers, that when the irrigation pumps are running in full in the Sacramento River, the river flows upstream, doesn't even flow to the river. So it's got real problems, but there can be connectivity The river used to meander across its floodplain. It had been lost. So reconnecting it unleashes this hidden potential for growth. And so you can just see it play out. Fish that are in the floodplain, at least in these years, it's probably waxing on and off. If they have the option to go between the river and the floodplain, growth is greatly increased, okay? So tap into the potential, but be consistent with what the potential of that system is. Don't try to make it more than it's capable of producing. Tap into the processes that's consistent with the site. The third principle, back to this idea of scale. In ecology, the problem of scale is everywhere. People like Ben that have suffered through my classes have heard this before. But the scale of action should be at the scale of the problem, okay? So again, in a system, this is from the Klamath River, Iron Gate Dam, slated to be removed, right? Places like this where we really know the root cause of the problem, and the problems on those systems are large scale, i.e. large main stem dams that are messing up the processes, messing up migration, right? It's the dams that are the problem. And so the restoration, what's difficult to stomach and is hard, is that the real restoration at the root cause means removing those dams, restoring those processes. And there's probably nothing that is more uplifting and sort of affirming than examples like the Elwha Dam removal. Up until recently, it was the largest dam removal process in North America. If you give fish a chance, lo and behold, you remove the dams, hadn't been upstream of the dams for over 100 years, the very next year fish are showing up. Because there was a group of fish below the dam waiting for that potential to be unleashed. And they do. It's like, connect the habitat and they will come, right? Give them a chance and they will come. And so Iron Gate and the other dams on the Klamath are slated to be removed in our lifetimes. Like, it's coming. So those will be the largest dam removal processes to date. And then the last one is that the actions for restoration need to have clearly articulated goals and objectives. And there needs to be monitoring. So this is brutal, and this is just so clear that our ability to understand what we should be doing with monitoring or with restoration or not is completely hindered by a lack of monitoring. Which is to say, did it work? Did it give you the results you wanted? For one, most people or most projects don't have clear objectives other than maybe like, well, we'll put some logs in a stream, that's our objective. But with regards to increasing production, increasing number of fish, often they don't have a goal. It's not monitored. Or the wicked problem is that it might be monitored for a few years, but because of those legacy effects, we know it takes a long time to see effects play out. And so this lack of monitoring literally, when you look at hundreds of studies, colleagues have done this work, piling together all these studies, hundreds of restoration projects, there's essentially no evidence that the restoration has done anything appreciable in terms of restoring abundances of fish. Have they not happened? Well, maybe it worked, maybe, but you can't see it because there's not monitoring, okay? So goals and monitoring go hand in hand. Okay, so those were the 5 principles that I wanted to touch on. I hope it's given you something to think about. If you're a new manager, hot off the plane, maybe this was useful. If you're an old manager or a practitioner, hopefully there's something in this for you. But I'm gonna end where I always end, staying optimistic. I am always so grateful and appreciative that salmon and people in Alaska are still connected. There are so many things challenging that relationship right now, and the relationships are strained. You could say they're under attack, whatever words you want to use, but they're still there. I've spent so much time in places outside of Alaska where those relationships are just gone. Or maybe they are cobbled together by something that's not quite natural. Whatever, we still have it. And at the core of that is that intact, functioning salmon-bearing ecosystems and that habitat that I've been talking about, and that you all are working so hard to study, maintain, protect, and is going to be the source of some great conversation over the next few days. So I'm going to leave you with that. Thank you so much for the introduction. Happy to take questions. I'll be around today and would love to chat, but thank you so much.